use, we are going to use a very similar, a very similar model for quantum neural networks, and then I want to explain what coherence theory has or can say about this kind of networks. So for all of you that you are not so familiar, okay, so classical neural networks just started as a copy, okay, of what it was our brain, okay, which is a network of more or less 10 to the 11 neurons, which are cells that they are able to receive, to process, and to transmit information via chemical and electrical signals, okay? And a quantum neural network, an artificial neural network, which is this first model, which was introduced almost 100 years ago, which is quite impressive. So it was a model, a mathematical model, which is a function which was aimed to a little bit to reproduce biological neurons. Okay, so these artificial neurons are elementary units of an artificial neural network. And what happens is you receive some inputs in the same way that it happens for a real neuron, so through the dendrites. And then you have the sum of them produces a kind of an output. And this is what in the biological network will be an axon. And I don't know why I'm perhaps sorry, because okay, so typically we say that we have a real neural network, which is our brain, and an artificial neural network. What it is a collection of neurons which are organized by shells, so to say, and you have some input and you have to have at the end some output. So the things that the most easiest or the most fundamental network or the simplest neural network is the Rosenblatt perceptron, which is a neural network which is composed by a single artificial neuron. And this artificial neuron, however, this is the basis of all complex neural networks and deep learning, how we understand it today. Although they are quite different, we will see it, but that was the initial thing. And what do you have? It's this mathematical function in which you have, you can understand it like an algorithm in which you have several inputs. Each of them, they are weighted by some weights Wi here. And then you have a sum of this, and then you decided to have an output, which can be 1 if this function, which is a linear function, it's larger than 0 or 0 if it's smaller than 0. And in the neurons, and also in the classical neural networks and in the biological neurons, we always assume that we have only 0 and 1s. So 0 means that there is not reaction, 1 that there is a reaction. And it was immediately very soon show that this kind of very simple perceptron can help or can use as a binary classifier, and even it could do some kind of logical operations, but not all of them, okay? And this is one of the reasons why these models, which were done like that, they were at some moment abandoned. So if we go a little bit further and we want to show what we are going to consider the state of a neural network, now we are going in a classical field, we are going to consider that it's a collection of spins or vectors, we can put it like that, okay? And we are going to assume that these are attractor neural networks, which are neural networks that they evolve on time. Okay, so as long as the time passes, this system, which is normally represented by spins, I will explain it a little bit more, tends to an attractor state, a stationary state. So what does it mean? Well, it means that we have, now we will see it, for instance, a collection of spins. These spins are classical, so they are 0, 1, so plus minus 1, it doesn't matter. They are connected 2 by 2, okay? And now the state of each spin normally evolves on time depending on the sum of the other spins, which are weighted here with some interactions, okay? And what it will happen is that this system will evolve until it reaches minimum of the Hamiltonian, of a classical Hamiltonian. And these models, Hopfield and all these people, and so on, why they realize is this is very close to systems what they are called spin glass systems, because these interactions, J, I, J, they are binary interactions. So normally, okay, so if we look at this Hamiltonian, which is a Hamiltonian that depends on time because the spins depend on time, so it has to be updated. And then we have that the only thing that it was demanded in these cases is that the interaction between two spins, I and J, it's symmetrical. And otherwise, these J's have to be random coefficients, which can be positive or negative. And then one decides to look what is the so-called a pattern, okay, which is a configuration of the spins. We have to think that we have all these spins, and there is a moment that the spins, they get ordered in a pattern, and we want to know how many patterns one can have. And the patterns correspond in this classical model to what is the associative memory. So you leave your collection of spins. This is a spin glass. The minimum cannot be found. This is NP hard because it has several minima. But it evolves to one of the minima. And when it reaches one of the minima, it stays there. And you use this as an associative memory. So if you have an initial input and then you leave your system evolve until it reaches one of these minima, it will reach the minima, which is closest to the initial input was closest to this one. And of course, there are a couple of things that one has to do. First of all, it's to look how many patterns this kind of network can have. So how many attractors in a spin glass model you have. And this is called the storage capacity of the neural network, which at that time it was shown that it's proportional to the number of neurons. So 0.14 doesn't matter. Nowadays, even with classical neural networks, one can reach better than that. Okay, so more than linear. But in general, this goes like a linear storage. So, and then one has to put a learning rule. Okay, so to have the whole thing complete, you have to have your system and you have to have a learning rule so that allows you to associate the patterns with the inputs that you have. And in the 80s, what it was used, it was this Hebbian rule of learning in which you have to modify which are the couplings in order to get the patterns that you want, where these patterns are random, identically distributed variables, and the possibility that the spin is up or down has to be 1/2. So with all this introduction, I want to say something, although I'm not going to work about that. So this was the state of the neural networks in the 80s. But it was a contribution that we considered that it was very important, which was given by Elizabeth Gardner in the 87. What she was proposing is what it's not important, it's to search really which are the stationary states of a model, but it's rather more important, it's to fix a model and see how many Hamiltonians they will have this state as an attractor. Okay, so if you have a lot of Hamiltonians, that means that this is a good pattern. But if you have very few Hamiltonians that will lead to this model, this is a very bad pattern because you will always have noise, distraction, and so on. And with this idea in mind, in some way, she was quite able to rephrase a little bit all the models of neural networks. So what we wanted to do first was to try to analyze the same kind of problem, but now assuming that we have quantum neural networks. And in the quantum neural networks, well, what we will have is that we have an input, which will be typically qubits. It doesn't matter, but it will be easy. So we have zeros and ones. And then we will have some operations, and we have a concatenation of operations. These are the hidden layers of the neural network. And at the end, we will do a measurement. And then we have to associate an output with the input if we wanted. So the first thing that we wanted to say is how we can treat from a quantum mechanical point of view or quantum information point of view this collection of attractor neural networks. So in our case, the state of the attractor quantum neural network will be the state of n qubits or qubits, it doesn't matter. And then instead of having all this evolution, because we have said that these attractor neural networks are a dynamical thing, we will have an evolution which has to be given by a completely positive trace preserving map, which was from our initial state to the final state. And it will be a stationary pattern if we put an initial state such that the action of the map on this initial state will be this state. So this is what we will define as a pattern. And the first question that we were interested in asking is which will be the associative memory of how many patterns quantum neural networks given by a map like that can contain. So we know, all of us, that a completely positive trace-preserving map has always a stationary state by definition, but which is the maximal number of stationary states that CPTP map can have, and which is the form of these maps was our first question. Okay, and this is something that we did together with people from ICFO, with and people from the autonomy in a collaboration, which was to say which is the storage capacity and the learning capability that a quantum neural network has. And we were applying this kind of Gardner ideas in the case of a quantum neural network. So we were assuming that the initial state and the final state, it's the same. And then we say, okay, our conditions will be, imagine that I have a basis, which is an orthonormal basis, which has n elements. And of course, the map has to be non-trivial. So it cannot be a map which is the identity, which by definition will have all possible states, but this is not interesting. And it has to be a map which is not necessarily unitary. So it doesn't come from the eigenstates of a Hamiltonian, because that will be also trivial. Okay. So under the most general restriction that, which is the map, okay, a CPTP map that can have the maximal number of stationary states. And this is what we were looking, and this is the form of the map, okay? And this is relatively straightforward to find how is this map. One has to use the Choi-Jamilowski isomorphism, because a little bit easy to work with a corresponding state, assuming that the state is positive, and it's a map that has a first part, which is, as you can see, is already a map that in the first part, so where mu, all these states are linearly independent. So this map has two parts. The first part is already kind of attractor, and the second part, which is a map which kills all the coherences, which is there. So it's a fully decoherence map, except that each coherence has to be killed at a different rate. Okay, so, and the conditions for the map to be completely positive, it's that this alpha mu nu, which are the complex numbers, which are the factors that kill the coherences, have to be smaller than 1. So it means applying this map several times, since the modulus is smaller than 1. Every time that I apply the map, it will reduce and reduce and reduce the coherences until we end in a map which is absolutely stationary. So, and this is the part which is important on this map. So what is then, when we finish these things, and we were working also in this Gardner program, so calculating which is the volume of all these possible CPTP maps that they have. Well, first thing that one can see, I have not said before, is that when one do that, what we observe is that how many states we have which are stationary. Well, we have a basis, so we have 2 to the n. Okay, so a quantum neural network can storage 2 to the n, so it has an exponential storage capacity, which is much higher than any classical storage capacity. You can demonstrate it in other ways. I mean, that was couple of papers before, that it was a very old paper, which was in the 80s, doing a short algorithm and looking for a kind of map. And later on, it was also a paper by Seth Lloyd and collaborators constructing a quantum Hopfield and using a phase amplitude channel to show the same. But these are concrete examples. Any map that has n stationary states, any CPTP map that has n stationary states has to be necessarily of this form. So we knew already that these attractor quantum neural networks have a power, a quantum advantage, in the sense that they are. It's not that this is, I have to say the truth, it's more kind of academic, because neural networks nowadays, they are not using this kind of perceptron, so you have to extend it. But we wanted to show that the storage capacity is much higher, and on top of that, that the volume of these maps is high. So it's not of volume 0. Among all possible CPTP maps that they live in one dimension, the volume of these ones it's important. So they exist. And looking at this form of the map, immediately we saw that maybe we can use coherence, okay, to understand better what are these quantum attractor neural networks. So quantum coherence, I just want to rephrase it very fast. No, it's like any other resource theory. The resource theory of coherence needs some free states, which is, as most of you know, you have a basis which is fixed, and in this basis you say that the state is incoherent, so it's a free state if it doesn't have, it's diagonal in this basis. Okay, so it's only populations and you don't have any coherence there. And these are the free states, and then one has to define the free operation. So all these maps that on an incoherent state remains incoherent. So, and a difference of in entanglement theory or other resource theory, okay, there are several kinds of free operations and there is a hierarchy, and you can define that, classify these maps by their Krauss operators, and then you define these maximally incoherent operators are the ones that the Krauss operators fulfill this relation. But there is also other classes, which are the incoherent operations in which each of the Krauss operators have to leave the state incoherent, not only the sum, but also all of them. And instead, there are also these strictly incoherent operations in which the invert relation also is fulfilled. And there are finally these genuinely incoherent operations in which when you apply the map to an incoherent state, it doesn't modify the state. Okay, so this is the strongest thing that it can happen. So not only, it cannot change, not even populations. So these are the free operations in coherence theory. And then one has to formalize the resource theory having measures. Like always, a measure you have, it's a function, it's a functional that it goes from a state which lives in the Hilbert space, in the operators of the Hilbert space, to a real number, which has to fulfill two things. It has to be faithful, so the coherence of an incoherent state has to be 0, and the coherence cannot increase under incoherent operations. And there are several measures. And then one has also an important thing, which is the maximally coherent states that we will use it. And one says that you have a maximally coherent state if you have a superposition of incoherence at the end means superpositions. So if the maximally coherent state will be the one who has all possible entrants in the coherence, and from this maximally coherent state you can obtain any other state possible. Okay? And in this sense they are important. So with all these tools at hand, what we wanted to know is what coherence theory can say about these attractor quantum neural networks. Okay, and this is the work that we did, which is in revision. And the first thing that we were saying is that, okay, so we consider now our map, which is this one. So this is the map which has n stationary states. And there are several questions that we can ask here. So first of all, we can ask how many times we have to apply this map so that we reach into a stationary state. So how many times we have to apply this map so all the coherences are killed. Okay. Another things that we can ask, so for instance, is which kind of maps are that from a coherent point of view. So it's very easy to see that the attractor quantum neural networks are described as genuinely incoherent operations, because if my initial state rho, it's just a projector into one of the orthogonal states of the basis, it cannot change that. Okay, so this we knew. And when we know that, another thing that we can ask is, well, how do you implement this kind of neural networks if you want to do it in the lab? So for the geos, okay, and not for all incoherent operations you can do it, we know that it's relatively easy to find which kind of unitary you have to apply to have this kind of map. And you do it using the Stein-Spring dilation. So you take your system, which is here symbolized by a series of qubits, and you take an ancillary system, and then you look for a unitary such that tracing over the ancillary system gives you the state of your system. And then we realized that if you want to implement physically, you have to apply this unitary AQNN, which is just of this form, is relatively simple, where it has your initial states times a unitary mu, which depends obviously on the coherences that we have from the map. The second thing that we wanted to say, it's what is the depth. of this attractor quantum neural network. That means how many times I have to apply my CPTP map into an initial state so that I end in one of the stationary states, okay? And we formulate it like that. So which is the coherence of applying the map R times such that the coherence of the final state is 0, okay? Because it's just an incoherent state. Okay, so the coherent power of a map is something that we can study, and it's defined in this way. So if I have a map epsilon, which in our case is our CPTP maps, we want to know what is the coherent power, and we have to maximize over all possible maximally coherent states, and then look which is the effect of the map on them. Okay, and doing that, and when used as a measure of coherence, for instance, the L1 norm of coherence, then we can show that the coherence power of these maps goes in this way. Okay, so where n is the number of initial qubits that we have. So of course, in general, this is quite it's a difficult problem, because if we are in n dimensions, we have a lot of coefficients, alpha, mu, nu, and optimizing over thousands of coefficients. As you know, it's a super difficult problem, but one can make some assumptions that all these the coherences will be equal, or it will be of two kinds of the coherence, and so on. So, and in this way, one can obtain how many layers, okay, one can has for a attractor quantum neural network, assuming, and we will assume here two things. First of all, that imagine that we do a small error. So at the end, we will have that the coherence after applying our map R times is not 0, but it's eta, which eta is a very small number. And then we will assume, for instance, that all the coherences, they are the coherence with the same power. Okay, so alpha mu nu equal to alpha, mu mu equal to alpha. So in this way, we show that, of course, the coherence power, okay, when we run that, so the number, the depth of the attractor quantum neural network, okay, goes relatively fast goes relative, so increasing GL, okay, so then we can find that we don't need to have so many layers in order to reach a stationary state. The other questions that we were asking, is it possible to enhance the performance of an attractor quantum neural network? So it can be, what do we mean by enhancing the performance? By enhancing the performance, we want to reduce the number of times that this map has to be applied in order to obtain a stationary state, which is an associative memory and helps us to classify different things, okay? So one way that one can enhance the performance of an attractive neural network is the following. It's say, okay, imagine in some stage of the neural network, okay, I up an ancillary state, and now I apply this ancillary state, okay, and then I trace this ancillary state to see if I can, in this way, the coherence faster than if I was doing my map only. And the result, it was not possible, because these maps are incoherent maps and fulfill, even if I put an ancillary state, that the power of the coherence will not change. Okay, this is assuming that we have a perfect, absolutely perfect neural network, that there is not errors in this attractive quantum neural network. So coherence cannot be used in any way to enhance the performance of an attractive quantum neural network, independently of the state that we put in our ancilla. So there is no way that putting an ancilla, we can reduce the coherences faster than if we don't put an ancilla and we apply the map to the whole system. And the other question that we wanted to ask, obviously, is that is it possible to enhance the performance of a quantum neural network using entanglement? Okay, and in order to do that, one has to do the same. So now we have to put in one of the layers that we have of our neural network, we have to put the state which has entanglement, okay, and then perform in one of the layers, apply our map times identity on this, and look if in this way, again, and we trace over this ancillary state, which is state which is entangled, can we enhance the coherence? So the coherence with this thing will be smaller and we will need less layers in order to reach a stationary state. And the reason it's neither, okay? So neither coherence, neither entanglement can be used in any case to reduce the depth of an attractive quantum neural network. So therefore, we are thinking, okay, let's consider that we have not a perfect error-free attractor quantum neural network, but assume that we have some errors on it, okay? So it's a more realistic. So instead, the map now depends on two parameters, epsilon and gamma, which means that there are errors either going to the attractor. So if I start by an initial state, which is mu mu, and I apply the map once, I will not reach my state mu mu, but I will reach the state mu mu plus other contributions mu mu. And then I will assume also that in the coherence part, okay, I will have some errors. So that we don't have a perfect error-free, and we have, on the contrary, a realistic attractive quantum neural network. And we want to see if in these conditions, either coherence or entanglement can help to reduce the number of layers that we need in order to reach a stationary state. And what we see is that in this case, so in the first case, our map was described by these genuinely incoherent operators, but in this case, the map is not anymore, because if I put a state which is incoherent, the result will not be incoherent. So it's another kind of function. So it's described by these strictly incoherent operators. And we repeated what we were doing. So how we can implement, or which is the kind of unitaries that implement this kind of error quantum neural networks. And in this case, can coherence of entanglement enhance the performance? And the results, I have to say that this was a kind of relatively simple errors, but even in this case, okay, so it's easy to describe which is the unitary that can be implemented. Not always is easy to find which is the unitary. So for CEOs, we can do it, but for instance, for EOS, it's not trivial, or it's not known how to find which is the Stein spring dilation. But again, neither coherence of entanglement cannot enhance the performance of this. Okay, so in conclusion, what I want to say is that what we have found is that the storage capacity of these attractor quantum neural networks is exponential in the number of nodes, while classically we know that it's linear in the number of nodes, or even quadratic, but never exponential. So clearly, the associative memory of a quantum neural network is huge compared to associative memory of a classical neural network, which is very good. Then we see that so if we start by an input which is given by an orthonormal basis, then the evolution of the network will always reach this storage capacity, which is maximal. And that such evolution can be studied really using coherence theory, although the results are still not very promising because it doesn't help very much, but at least we can understand how it works and also how that can be implemented physically in a lab. And we saw that if the quantum neural network is error-free, so it has really n stationary states, the map can be described by a genuinely incoherent operation. We know how to implement it physically. We know how to calculate the depth of such quantum neural network, and also which are some other things related to that. And we know that coherence and entanglement cannot enhance the performance of such a quantum neural network. And we saw that if we put some errors in both parts of the map, in the part which is, let's say, the associative memory and in the decoherences, the system corresponds to a CEO, so it can be described also with coherence theory. We know also how to implement it physically. To calculate the depth is a little bit more complex, but we can do it. And still, coherence and entanglement cannot be used to enhance. So we have as an open questions the following. So what happens if we consider other classes of faulty attractive quantum neural networks? So in which the analysis becomes much more complex, and this is the reason that we were doing these simple errors. What happens if we consider completely general attractors? So will be the evolution of the network look like different things? So can be coherence theory studied to used to study all these kind of evolutions of quantum neural networks. And well, our initial idea was to kind of link quantum machine learning in these cases with the tools that we know from quantum resource theories, and coherence looked for us at that moment the most promising one. And with all these things, I would like to thank you for your attention.
Thank you very much, Anna, for this extremely interesting talk. So we do actually have quite a large amount of time for the questions. So Gerardo, please.
Hi.
Yeah, very nice talk. Very interesting. So first question is, so if coherence doesn't help in this particular model, where does the advantage of the quantum neural network come from? Can you pin it down to some other resource?
Coherence, it's not that it doesn't help. Coherence help because obviously you have to have, so if you have just that there is, well, I have to say, I have to answer properly. There is things in which it helps. So for instance, to calculate the depth of the neural network, you need this coherence theory, okay? If not, it's impossible to calculate it, and it's super complex. So that gives you a very easy way to say, okay, I need to pass my network several times. So this is good. And we think that coherence theory will help, okay? But not in these very simple cases of neural networks in which you have either no error, and the map is very simple because it's a map which is a completely the coherence map, with on top of that, to treat it analytically, we have to put all the coherences equal, okay? So this is a very restricted case. But in more general maps, which you end up having still this exponential memory, we think coherence will help at this, okay? But we don't know it yet.
Yeah, looking forward to the updates then. Thank you.
Thanks.
More questions or comments? So Domenico Pomarico, please.
Yes, thank you very much. I would ask you just a curiosity about the open questions you mentioned at the end of your talk. Can I think of a more general class of neural network if we include also some local operation and classical communications after the application of each map?
Yeah, I understand. I don't know. We never thought about that. Probably, I don't know. I mean, we had the feeling that, well, I don't know, for all of you that work in coherence theory, you know that even Stein string dilation in some of the incoherent cases is difficult, but we never thought on using as a resource to have some classical communication there. We have not considered it. I don't know. I cannot say. Maybe. I don't know.
Okay, thank you very much.
And still more question. We do have plenty of time still.
I have small technical remark. Well, indeed, very interesting results. Just one comment. You mentioned this condition for complete positivity, right?
Yes,
one plus
right.
alpha.
One has to do everything. Yes. You are completely right. Yes.
This is necessary, but not sufficient.
No, it's necessary, but it's not sufficient. So you have a big matrix, so you have to do some condition. Okay. Yes, you are completely right. And thank you, because we put it like that very fast. And yes. So even to check the complete positivity of the map, it's complex, all right? Because we are talking, even if all the alpha, so the problem, just want to say the problem is not simple, all right? So I present it like that. But as Darius was saying, indeed, so you have a matrix which is n by n. Okay, so you know that, but then you have to use, I think, the only way that you can do it, I don't know, maybe there is others, it's really using this Sylvester condition of minors and check all the minors that are positive. Yes, so this is kind of complicated. Okay, yes, and only in the case, only in some cases you can solve it analytically. That's also the reason that I'm saying that if you put some errors, okay, so let's put it like that, we put some errors in which we could check this condition. easily, because your map, when you have a quantum neural network with errors, the map has to be completely positive also, no? But if you generalize to other errors which are absolutely equally probable, okay, so it's not that the errors that we put are physically more relevant. No, are mathematically easy to solve, to check the completely positivity. That's the reason that we don't know if with another error, all these results that, well, we suspect not. We suspect that there are other kinds of errors in which entanglement and coherence will help. This is our idea, because then we will move from this paradigm of being geos and ceos and go to something where it's a little bit more general, and then it can help. But it's difficult. It's difficult.
Okay. No. Everything is clear. Thank you.
Let me also ask a very simple question. I mean, so you had this restriction assumption about the pure linear independent attractors forming a basis.
Yes.
So was this for the sake of convenience?
No, this is necessary, because if it was not like that, which is also something that we originally didn't realize, if it was not like that, so imagine that you can do it even if you have, so at first we thought that it's enough that we have states which are, that they are linearly independent instead of being orthogonal, okay? But if it was the case, so I have to say that unfortunately we put it in the paper and then we did an random. If that was the case, that will mean that you can distinguish states which are not orthogonal, because you will end up, so your neural network will end up, okay, telling you or being as having as attractors states which are linearly independent but not orthogonal. So this is not possible. No, it will be a way to discriminate between states which are not orthogonal. It's not possible. So necessarily your states has to be, you have to use n states which are orthonormal, or linear combinations of them, of course, but orthonormality has to be there by principle, by default. So all the attractors that you have, so any CPTP map, okay, that has n, also 2 to the n, okay, stationary states, these states correspond to a basis. Okay, it doesn't matter which basis, but they have to be orthogonal, yes.
Right, yes.